Oh, hi, my mathematical friends. It's Mr. Jennings, your humble math servant. And today we are looking at function notation. What an important topic to have on this snowiest of days. So, function notation is going to be something we're using throughout the course. In your textbook, you're going to see a lot of y equals, but there's also f of x that we're introducing today, and these are basically the same thing, but this one is introduced at the grade 11 level. It's much more powerful and convenient to learn this notation for more advanced mathematics. You want to know this. Okay, so it uses a letter as a label. In this case, f is the sort of standard or default, so it means a function. Okay, and we read this in this way. F of x is equal to 2x plus 5. That's how we read that. F of x is equal to 2x plus 5. Another way to extend that out is you can say a function of x is 2x plus 5. This is basically the same thing as saying y equals 2x plus 5. If we were to graph f of x as 2x plus 5, it would still cross up here at plus 5 and have an upward slope and a downward slope. That is that line. It is also y equals 2x plus 5. It's the same thing. But you're going to like it if you learn it. Now, f of x is quite common. It's the default, but then we just go alphabetically. G of x, h of x, j of x. I avoid I of x. It's weird. But we can use other ones as well that are actually quite descriptive. So here are some descriptive functions, and I like these examples because they give us a real intuition for how this notation works. So area is a function of radius, or a of r is pi r squared. If I have some circle here, okay, with some radius r, and then I change the radius, I'm changing area. And this is a function. It passes vertical line test and all of those things. So area is a function of radius is one of our functions here. This one here is volume is a function of edge length. I have a little math assistant here who's joining me.
I finished the book.
Oh, good. So here is my cube. Okay, and then if I tell you that E is the edge length for one of those edges, well, it's E in all dimensions, right? And to find its volume, well, its volume is a function of that edge length. It's just equal to E cubed. So that's where volume is a function of edge length. That's that function. All right. This one here, distance is a function of time, or d of t. Okay, distance is a function of time, refers to the movement of a falling body and how quickly and how far it's moved. So 4.9 times time squared, because it accelerates as time goes forward. Okay, so these are all functions that are actually connected to the world. Note, it's a special notation. It does not mean that we're multiplying f and x. I know you're thinking, like, if I have 3x, that's equal to 3 times x. Okay? But f of x is equal to f of x. It's not multiply. It's just a function of x. So we're never multiplying here. It's not something we do. So I would encourage you to think of it as like a subscript, that little bracket x. Okay? It's simply replacing y equals in our functions. It has a different way of talking about it. We can even label the axes of the graph, like this is x, and this is the f of x. That's the output, and this is the input. Basically, a function just takes inputs, does things to them, and then makes an output, which was f of x. And here's how we use this notation. We can actually put in values for x there. So if I know f of x is equal to x squared minus 5x plus 1, and I want to calculate f at 0, that's a set of instructions. That's a set of instructions saying, please put 0 in for x wherever you see it. So I'm going to substitute that into brackets wherever I see x, and then evaluate. So that tells me f at 0 equals 1. And I can even start working on putting that onto a graph. At 0, this is 1. So there's the point, 0 in the x, 1 in the y. Okay, and then f at 3, well, let's go. I start with f of x is equal to x squared minus 5x plus 1. Pause the video and see if you can work it out the same way I do. Oh, you're back. Okay, good. So you probably put 3 into brackets there because we're looking for f at 3. Okay, so now this is a set of instructions saying substitute 3 in for x. 3 squared minus 5 times 3 plus 1 gives us 9 minus 15 plus 1 gives us minus 5. So this is the point 3 minus 5 down here. Okay, that's the point 3 minus 5. And that would be on this parabola as well. Looks something like this. I don't know where it turns around, but it turns around like this. It turns around at 2.5. Actually, I drew a really good graph. Yeah. And then it's going to go up here. So I predict when I put in minus 2, it's going to be pretty high. Let's see. Let's see what it gives us. Here's another trick. If we want f at minus 2 and you don't care about your rough work, you can just go ahead and selectively erase like that. And then substitute in, say, minus 2. Wherever you need it. Cool, eh? So minus 2 squared is 4. Minus 5 times minus 2 is 10. And so that gives us a point 15. 4 plus 10 plus 1 is 15. So this up here is the point minus 2, 15. And we've basically got 3 points on this graph already. Cool, right? Okay. Here's a linear function, g of x is equal to 3x minus 2. Okay? And we've been asked to determine g at 2x plus 1. That's kind of rough, Miss Metherall. Starting with that example. Let's start with this example, everyone. I can do g at 1, and that would equal 3 times 1 minus 2. That would equal 1. 3 minus 2 is 1. Let's write it all out. Oh, my phone isn't silent. I bet you heard that. Don't tell on me, okay? So g at 1 is equal to 1. Okay? But, so that's g at 1 equals 1. Happens to be. Now, we could also substitute in something like a variable for x. You're going to be like, why did you do that? Okay? Instead, g at a would be 3 at a minus 2, so that's equal to 3a minus 2. That is to say, we could have some data set that we want to feed x, and so we could put like a different label in there and just change the label. G at a would be 3a minus 2. But what if I put in this for x, and I substitute x with 2x plus 1? This is actually going to create a new function, and this is what it will look like. Okay? It's the same, but some of you will be confused. G at 2x plus 1 will equal 3. And then wherever I see x, I put in what I'm substituting in for x. And then I just keep the other machinery of the function around there. So that would be 2x plus 1 gets substituted in for x. That's all. And then we can simplify and tidy it up. Okay, so then we will get g at 2x plus 1. Note, that's just a little label. I'm not changing that or multiplying or anything. That's the new label. That's the new function. G at 2x plus 1 is equal to 6x plus 3 minus 2. That minus 2 just comes down. So that's equal to 6x plus 1. That's the new function g at 2x plus 1. That's how we do these things. You just put in for x what the instructions say to put in for x, even if it's itself another function. That way you got functions within your functions, bro or madam. Bro or madam. Has this sentence ever been said? And I've excluded non-binary. Bro or madam, or not falling into bro or madam category people. Okay, we can also have like a function like f of x and give you points this way, where we would say f at 2 is minus 1. So that would be the point 2 is the input, minus 1 is the output, and it would be down here. Okay, that's 2 minus 1. Or if we have f at 0 and 7, so this is the input, this is the output. So that's 0, 7, way up there. 0, 7. And then this one is minus 4, 3. So it's over here. Minus 4, 3. Okay, roughly. That's how I would translate these into coordinate points. We can even go backwards from a graph and figure things out. Here's a function f of x. And something I know about f of x is that when we're looking at minus 3, we go into 3. Here's minus 3 in the x. We go up and find the value. That's plus 3. Okay, so this is 3. That's the point minus 3, 3. So I can look at a graph and tell you, when x is minus 3, the output is 3. The value of the function will be its y value, okay, the output. X when f of x is equal to 0. Okay, cool. When does this function equal 0? Oops, equal 0. Oh, right there. So that's going to be x is equal to minus 5, or you could say f at minus 5 equals 0. We can go backwards and forwards too. F at 2, so here's when x is 2, that's over here. I go up and I find it. Oh, that's 2. Okay. And x when f of x equals 9, let's find it. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Go find the function. It's over here. That's 1, 2, 3, 4, 5, 6. So x equals 6 and f at 6 equals 9. Thanks for that interruption. Alright, so that's how that do. Why did I leave you so much space there? I don't know. I could probably fit this on, but it's already a 4-pager, so 4 pages is as good as 3. Okay, so here we go. We are now going to create our own function. This is another thing that you can do. So I want a function for the volume of this copper wire. Okay, so the copper in a cable. Okay, it's going to be a function of length, because as it gets longer, its volume increases linearly. All right, and I know that volume of a cylinder is equal to pi r squared times the length of the cylinder, or the depth of the something, whatever, some other dimension. Okay, that's our formula. It's the cross-sectional area multiplied by how long it is. Here we're told that the radius is 2 centimeters, so we're pi 2 squared L, which gives us 4 pi L. So that's our function. 4 pi L. What I can do, this is a little math machine. And I can feed this machine values of length, and it will tell me the overall volume of that copper wire in the cable. Okay, so if I want to know the volume at 15, and this is going to be expressed in centimeters cubed, because this 4 is actually 4 centimeters squared, and the length is in centimeters, so we will get centimeters cubed, as we should for volume. Volume is measured in cubes. Okay, so V at 15 is equal to 4 pi 15, which would be equal to 60 pi, and I would be quite comfortable leaving it that way, but gosh, if you want to say 180, probably 188.7, I don't know, let's find out. See how good my multiply by pi in my head without really doing it is. Okay, so we got 60 times pi equals 188.49, not 0.7. Gosh, what an egregious error. Okay, so we can say 188.5. But if you can also just say 60 pi, and that's pretty much exactly accurate. Okay, so, and that's in centimeters cubed. So what does this mean? So now we need a little sentence showing that we understand what our function has done. What? Huh? Hey, come on in. So V at 15 equals 188.5 centimeters cubed means that when the... No, you don't get to take that. Means that when the cable is 15 centimeters long, there is 188.5 cubic centimeters of copper in it. That's what it means. Okay, so let's go. I'm almost at the end here. All right, V at L is equal to 500. Oh my goodness. Well, this one is a trickier problem. This is like I tell you the volume and then you have to tell me how much copper that would be. I can tell from this it's going to be longer than 15 because 500 is bigger than 188.5. Many of you already know that. So to solve one like this, you say, well, you just write out your function. Okay, V is a function of L, and it's equal to 4 pi L. But I'm told 500. 500 equals 4 pi times length. Now I want to solve for length. In order to do that, I need to divide by whatever length is being multiplied by, because right now it's being multiplied by 4 pi. So let's divide by 4 pi. That's going to be 125 divided by pi. Do you want me to guess? A little less than 40? I think it's a little less than 40. I can guess 39. Okay, so let's check it in the calculator. Doing these little guesses makes math fun, okay? I'm gonna have fun when I see how wrong I was or how right I was. Okay, so 500 divided by, put it in brackets, 4 times pi, and the bracket equal, oh, that's really close to 39. Yeah, it's closer to 40 than 39. I'm learning. Okay, so we need 39.8. 39.8 equals L. So what does this mean? This means, yeah, no, I do want that. This means that when the volume of copper in the wire equals 500, then it's the length of the wire is just shy of 40 centimeters. Just shy of 40 centimeters. We were almost there. We were almost to 40. Those of you who wanted to get all the way to 40, sorry to disappoint you. We were just shy. Try these questions, okay? Don't call them homework. Call them check your understanding questions. Get into, you all brought your textbooks home, right? You sleep on them so that the math seeps into your brain at night. Try these questions. If you like thinking, try those questions. And any questions that you have for me, ask me on Friday or ask me in the D12. And anyone that emails me the words, "the ostrich eats Skittles," will get a huge high five from me and maybe a prize. Email me, "the ostrich eats Skittles." Bye for now, everyone.